A reactive robot policy maps the current camera image directly to a motor action. That shortcut can reproduce familiar demonstrations, but it never has to answer the physical question underneath control. If the robot takes this action, what will happen to the scene? LingBot-VA 2.0 inserts that missing consequence. It represents the current state, predicts a future visual state, and then decodes the action that connects the two. After execution, a new camera observation corrects the prediction. The central idea of the paper is that representation, pre-training, and inference should all be built around this closed-loop sequence from the beginning. Before discussing control, we need the mathematical object the model predicts. A raw video is a tensor O with t time steps, height h, width w, and 3 RGB channels. Processing every pixel directly would be expensive, so an encoder recompresses the video into latent tensor Z. Equation 1 records both directions of this compression. E maps O to Z. The latent has t prime temporal positions, spatial dimensions h and w, and c channels. Decoder D maps Z back to reconstruction O hat. The approximation sign reminds us that compression is lossy. The temporal downsampling factor f sub t is t divided by t prime. If f sub t is 4, one latent transition represents 4 original time steps. The spatial factor f sub s is h over h. Equivalently w over w. These factors matter later because a robot must align several low-level controls with each transition in latent time. Now consider how a generative model learns to create Z. Start from Gaussian noise epsilon. Connect epsilon to clean latent Z with a straight path parameterized by s at s equals 0. The point is pure noise. At s equals 1, it is the data latent. Intermediate Z superscript s is a weighted mixture of the two. The network V theta receives the interpolated latent, the flow time s, and text condition C subtext. Its target is Z minus epsilon, the velocity pointing from noise to data along this straight path. The expectation averages squared velocity error over data examples, noise samples, and flow times. Once trained, integrating this velocity field transports a new noise sample into a video latent. Terms explained on screen. O. Raw RGB video tensor. E and D. Encoder and decoder. Z. Compressed video latent. T prime. H. W. C. Latent dimensions f sub t and f sub s. Temporal and spatial compression factors. Epsilon. Gaussian noise. S. Flow time coordinate between 0 and 1. Z superscript s. Noisy interpolation point. V theta. Learned velocity field. C subtext. Language conditioning. Video latents advance at a compressed temporal rate, while robot controls are recorded at the original high frequency. The first task is therefore alignment. Let U sub I denote one raw motor command. Equation 3 groups f sub t consecutive commands into action chunk A sub t. That chunk covers exactly the time between visual latent Z sub t and Z sub t plus 1. With t prime latent states, there are n equals t prime minus 1 transitions. From now on, the symbol A sub t always means this block of controls, not one command. A conventional video generator sees every frame in a training clip. Closed-loop control cannot. When the robot is at time t, future observations do not exist yet. Equation 4 writes the future video distribution as a causal product. At every step, Z sub t plus 1 depends only on Z through time t. The notation Z less than or equal t means the observed or previously generated latent history. The absent term Z greater than t is the whole point. Present computation cannot inspect the future. Now extend the factorization to actions. The first conditional is the world model. Given visual history and actions before t, predict the next visual latent. The second conditional is inverse dynamics. Given the same history and the next latent, infer action chunk A sub t. This orders reasoning as history, then consequence, then action. The two conditionals are trained as separate flow matching problems. For video, epsilon sub t superscript z has the shape of the next latent. Interpolation z sub t plus 1 superscript s mixes that noise with the clean next state. The video expert predicts its velocity while conditioned on causal state action history. The target is the clean latent minus noise. The action branch is parallel. Noise epsilon superscript a has the shape of the action chunk. The action expert sees the noisy action, flow time, causal history, and next visual state. Its target is a sub t minus action noise. Lambda sub act controls the relative action weight, and the total video action objective is video loss plus lambda sub act times action loss. At inference, integrate the video velocity field to obtain z hat sub t plus 1. Then integrate the action velocity field, using that predicted consequence, to obtain a hat sub t. The symbols v are overloaded in the paper here. They refer to samples obtained after integrating the respective velocity fields. This two-expert sequence is the core that later modules scale, supervise, and accelerate. Terms explained on screen. U sub I versus A sub t. One control versus a transition-aligned chunk. Z less than or equal t. Available visual history A less than t. Actions already executed before the current transition p theta. Causal model distribution. V theta superscript video and action. Modality-specific flow fields. Z hat and A hat. Integrated future and action samples. Lambda subact. Action loss weighting. A reconstruction-only tokenizer preserves whatever helps redraw pixels, including detail that may be irrelevant to control. LingBot-VA 2.0 adds a second requirement. The latent must align with a frozen visual foundation model. The encoder is a causal vision transformer. The first frame uses spatial patches. Later frames use spatiotemporal tubelets. One branch decodes the latent back to pixels. Another projects the latent toward teacher features from a frozen perception encoder. The reconstruction objective has three terms. The L1 term directly penalizes pixel error between O and O hat. The perceptual term compares higher level features, preserving structure that raw pixel distance may miss. The GAN term encourages realistic detail. 3 lambda coefficients balance those goals. For semantic alignment, G of O is the frozen teacher representation. W sub align projects tokenizer latent Z into the teacher feature dimension. The AVG operator pools over time, converting both sequences into clip level features. Their squared L2 distance becomes the alignment loss. Temporal pooling aligns meaning without forcing every latent frame to discard local information. The complete visual objective is reconstruction plus lambda sub-align times alignment. Reconstruction keeps the latent decodable. Alignment organizes it around semantic distinctions that language-conditioned control can use. This directly addresses the paper's claim that pixel-oriented video latents are a poor foundation for precise instruction following. The tokenizer next extracts an action-like variable without using robot action labels. Freeze the visual tokenizer and take consecutive semantic states Z sub t and Z sub t plus 1. Inverse dynamics encoder Q phi maps the pair to latent action L sub t. Its dimension D sub L is much smaller than the dimension of a visual state. This bottleneck is essential. If L were large, it could copy the next frame. Because it is small, it must concentrate on the transformation, motion, contact, object displacement, and other control-relevant change. Forward model FC must reconstruct the next state from Z sub t and L sub t. It predicts transport map K sub t and residual delta sub t. K moves information across spatial latent tokens. This is suitable for an object or hand changing position. Delta captures whatever transport alone cannot explain, such as newly exposed surfaces or non-rigid change. Training checks the transition in both directions. The first squared error compares forward prediction z hat sub t plus 1 with the true next latent. The second compares reverse transport prediction z hat sub t with the true previous latent. Summing across t gives latent action loss L sub L. The final tokenizer emits paired visual and transition sequences, z from 0 through n, and L from 0 through n-1. In stage 2, the paper writes A sub t as equivalent to L sub t. This conversion is what lets unlabeled web video contribute action-relevant pre-training signal. Long horizon tasks need a different timescale from motor control. A pre-trained VLM planner runs in the background at roughly 2 Hz. It reads the episode goal, 3 recent keyframes, and completed subtask history. Its vision tower stays frozen while LoRa adapts the language side to a strict structured output. The asynchronous buffer contains 4 fields. Done tells the scheduler whether the subtask has finished. Instruction is the compact command used during policy training. Generation instruction describes expected motion and interaction. Local scene description grounds the instruction in the current layout. The low-level policy reads the latest buffer entry only at a chunk boundary, so planner latency does not stop the robot. Planner training uses boundary crossing examples. Inside segment G sub I, done is false and the target repeats the current subtask. Just after crossing into G sub I plus 1, done is true and the planner must infer the next subtask from vision, the global goal, and prior history. The interface must match training exactly, otherwise the policy receives out-of-distribution text at deployment. The low-level model is a 30-block diffusion transformer trained from scratch. Video and action use different widths because their modeling burdens differ. The semantic tokenizer emits 96-channel visual latents. A 1x2x2 patch embedding produces video tokens of width 2048. The action input uses a unified 30-dimensional layout, then a bias-free projection lifts it to width 768. Both streams communicate in a shared attention space of width 3072. 24 heads times 128 dimensions. Video queries, keys, and values project from 2048 to 3072. Action projections lift 768 to 3072. Attention outputs return to their own stream widths. Outside attention, the video feed forward path is sparse Mo, while the action feed forward path remains dense. The lower triangular mask enforces block causality. During training, chunk sizes resampled from 1 to 4 latent frames and the history window from 1 to 64 chunks. Evaluation uses 2 latent frames per chunk and a 64 chunk window, with probability 0.5. Small noise replaces clean context frames, reducing the gap between teacher-forced training and auto-regressive deployment. Visual dynamics need substantial capacity, but activating a dense 13 billion parameter network for every token would undermine fast control. LingBot-VA 2.0 makes only the video feed forward path sparse. After causal attention, one hidden visual token H enters the router. Gate vector G sub I produces inner product G sub I transpose H. A sigmoid turns that logit into positive score R sub I. Repeating for n sub E experts gives score vector R of H. The main model uses 128 rooted experts. The model does not choose the top experts globally in one operation. Experts are partitioned into groups. Group limited top K first keeps promising groups, then selects K experts inside them. Bias B is added only for selection and will later be adjusted for load balance. The chosen set R of H contains exactly K equals 8 experts. For each selected expert, alpha sub I is its sigmoid score divided by the sum of selected scores, multiplied by rooted scale gamma. The denominator includes only experts in R of H. This normalizes competition inside the active set. Every token receives shared transformation E sub shared of H. It also receives a weighted sum over the selected rooted SWI glue experts. The shared expert handles common computation. The rooted experts specialize. This produces approximately 13 billion video parameters but only 1.9 billion active for a token. Without balancing, a few experts can absorb most tokens. Let C sub I be the observed token count for expert I and C bar the mean V sub I is positive for an overloaded expert and negative for an underused one. The correction bias moves in the opposite direction, centered by the mean sign across experts. Eta sub LB sets the update rate. This method changes selection bias instead of injecting a large auxiliary balancing gradient into the flow matching objective. The paper retains only a light monitoring regularizer. Sparse capacity is therefore added without changing the causal attention graph. Teacher forcing supplies a clean ground truth history. At high frame rate, the nearest future chunk may look almost unchanged. The model can reduce loss by preserving appearance instead of understanding trajectory dynamics. Equation 20 is the myopic conditional. Predict only Z sub t plus 1 from visual history and previous actions. This target is necessary, but not sufficient. Multi-chunk prediction adds K future horizons. Main feature extractor F theta produces H sub t superscript 0 from the causal prefix. MCP head K predicts Z sub t plus K using feature state H sub t superscript K minus 1. Later heads receive the previous head's internal feature, not a clean future observation and not an autoregressively generated frame. This distinction forces the representation at time t to encode information useful across a longer trajectory. Each horizon is itself a flow matching task. Z sub t plus k superscript s is the noisy target. V sub theta k superscript MCP predicts its velocity conditioned on the inherited feature. The clean velocity target is Z sub t plus k minus epsilon sub t superscript k. A larger time step shift weakens clues from the noisy target and forces greater reliance on the backbone. The three horizon losses use weights 0.5, 0.2, and 0.1. The nearest auxiliary future has the strongest weight. The farthest still supplies a meaningful trajectory constraint. Hidden states from backbone layers 3, 11, 19, and 29 are fused before the heads. The heads can be removed after training, so their representational benefit has zero cost in standard inference. A short command may identify the goal without specifying a rare manipulation procedure. LingBot-VA 2.0 therefore accepts a human demonstration video as an external visual prompt. The semantic tokenizer encodes the entire demonstration into Z sub ICL. Every step of the robot rollout can attend to this prompt. Robot side attention remains causal. Z sub T cannot inspect later robot states. Full access to a separate demonstration does not reveal the robot trajectory's own future. Equation 24 adds Z sub ICL to both factors. The future robot video distribution uses the demonstration to understand how the procedure should unfold. The action distribution uses the same prompt when decoding the action that realizes each transition. Object instance, viewpoint, and scene layout need not match. The paired videos need shared task semantics. The data pipeline creates more than 50,000 pairs spanning over 5,000 tasks. It samples a robot task, edits the first frame into a plausible human setup, generates a human manipulation video, and filters it for semantic preservation and physical plausibility. Human video is diverse and inexpensive, but human hands and robot grippers do not share a native action space. A superscript H denotes the original human annotation. Map-Phi preserves 2/6 degree of freedom hand root poses and converts each hand's finger configuration into one scalar virtual parallel gripper opening. The result A superscript H occupies the same bimanual end effector slice A as a robot action. Missing channels are zero padded and masked. This resolves the layout mismatch, but not the motion gap. A human wrist and robot end effector have different kinematic distributions. Domain-specific encoder E sub D maps human or robot action history into the shared model. Shared action expert V superscript act combines that history with visual history and predicted next state. Decoder P sub D maps the shared representation back into the domain's low-level action parameterization. Domain D is either R for robot or H for human. The co-training objective sums expectations over robot dataset D sub R and human dataset D sub H. Both domains supply the same future video loss. Their action losses pass through their own heads. The expensive video expert, action expert, and causal attention are updated by both datasets. At deployment, the system retains only robot encoder E sub R and decoder P sub R. Human co-training expands the learned dynamics without adding execution cost. The model is trained from scratch, but not as 3 isolated stages. 5 tasks remain active on one semantic latent space and one causal DIT. Text-to-image establishes semantic grounding. Text-to-video learns general motion. Text-image-to-video action specializes toward control. In-context learning trains visual prompting. Human-robot co-training transfers egocentric interaction. T is the 5-task set. TAU is normalized training progress. Pi sub I of TAU is the probability of drawing task I, and all probabilities sum to 1. L sub I is that task's loss. Early training concentrates probability on text to image, then shifts toward video, and finally toward video action tasks. Earlier objectives retain a small non-zero probability, reducing catastrophic forgetting. The data combines web-scale imagery, thousands of robot hours, 65.4 thousand egocentric human episodes from more than 600 operators, more than 3,000 scene task combinations, and over 50,000 ICL pairs. Training uses rectified flow with time step shifts 2 for image and web video, 5 for robot video action, 10 for MCP, and 1 for actions. Muon updates transformer matrices, ADAM updates embeddings, normalization, biases, and heads. The implementation uses a 2000-step warm-up, unit gradient clipping, BF16 computation, FP32 gradient reduction, activation checkpointing, and FSDP sharding. Even an efficient model can create a serial bottleneck. If the robot waits for inference and inference waits for the next observation, model latency becomes control latency. Foresight reasoning separates prediction and execution. While action chunk A sub t executes, the prediction stream starts from grounded cache C sub t, appends that action, imagines its consequence, and prepares A sub t plus 1. C sub t contains KV cache entries grounded in real observations through time t union with A sub t creates temporary look-ahead context. On line forward model FDM sub theta is the policy's video expert, not the frozen tokenizer FDM. Its output z hat sub t plus 1 is the imagined consequence used to decode the next action. Purely recursive imagination would drift. When the real next observation arrives, it is encoded as z sub t plus 1 and overwrites the stale imagined cache entry. Prediction provides speed. Feedback preserves closed-loop behavior. The grounding loss trains exactly the conditioning used at deployment. The critical context is A less than or equal t. It includes the currently executed action. By contrast, the ordinary video loss uses only A less than t. The target remains the flow velocity from noise to the true next observed latent. This makes the video expert a genuine action-conditioned forward model for the transition that is currently unfolding. The original post-trained policy numerically integrates the video flow for 5 steps and the action flow for 10. Real-time deployment distills both to 2 evaluations. Discretize flow time into grid S0 through SM, with SM equal to 1 at the clean data endpoint. Starting at noisy point x of S sub n, the frozen teacher velocity v theta takes 1 Euler step of size S sub n plus 1 minus S sub n. The result x hat at the adjacent time lies approximately on the same probability flow trajectory. Student F sub 11 maps the earlier noisy point directly toward a clean endpoint. Target F sub 11 minus is an exponential moving average copy with stopped gradients and receives the teacher advanced point. Distance d is squared L2. If both inputs lie on one trajectory, consistency says both networks should predict the same clean endpoint. Distillation reduces video sampling from 5 to 2 steps and action sampling from 10 to 2. 3 systems layers remove the remaining latency. FP8 tensor RT accelerates transformer linear layers while the head and tail remain BF16. Paged and ragged KV caches plus flash infer avoid repadding long histories. Cached bindings, tensors, cross-attention states, and metadata remove repeated host preparation and synchronization. The measured progression is 927 milliseconds per chunk at baseline, 466 after distillation, 369 after low precision compilation, 272 after attention optimization, and 142 after runtime reuse, with 32 low-level controls per chunk. Asynchronous control increases from 35 to 225 Hz, a 6.5 times speedup. On RoboTwin 2.0, LingBot-VA 2.0 reaches 93.8% success in clean scenes and 93.4% under domain randomization, averaging 93.6%. That is 14 percentage points above Pi 0.5 and 1.4 points above the earlier LingBot-VA. The clean to randomized gap is only 0.6. The tokenizer ablation isolates representation quality. Replacing the WAN 2.2V raises the 50-task average from 78.0 to 86.6 on easy and from 76.0 to 83.1 on hard. At prediction horizon 3, easy success rises from 67.2 to 92.0, showing that semantic tokenization matters more as prediction extends farther. MCP improves optimization speed. At 50 frames per second under randomization, it leads by 29.7 points after 5,000 steps. It matches the baseline's 45,000 step result after 20,000 steps. a 2.3 times speedup. Real-world evaluation uses one generalist checkpoint trained on 20 demonstrations per task. It covers pen collection, fruit sorting, drawer tidying, and plate handover. In a separate ICL study, the model trains on 4 scene tasks with 15 demonstrations each, then transfers human video procedures to 4 unseen object and container combinations without test time parameter updates. The paper's gains do not come from one isolated component. The semantic tokenizer aligns world state with visual meaning. The latent action bottleneck extracts transformations from unlabeled video. Native causal dynamics match the forward direction of closed-loop control. Sparse experts expand capacity. Multi-horizon, visual context, and human co-training objectives enrich what the representation must predict. Foresight overlaps inference with execution while real observations repeatedly correct the rollout. Together, those choices turn a video generator into a fast closed-loop controller. The paper also names 3 limitations. First, planner and policy are trained separately through a fixed interface. Joint training may improve long-horizon consistency. Second, latent actions come from passive video. Interactive or reinforcement signals may sharpen their control meaning. Third, embodiment coverage remains centered on bimanual manipulation. Broader robots and environments are still needed. The final takeaway is architectural. Design the representation, causal dynamics, and runtime for embodiment from the beginning.